In this session, we are going to have contributions from Alexandru Todor, Simon Clark, and Alexander Behr. And what is the whole framework? You will have seen similar messages in previous sessions, I presume. Be aware that the session is recorded. If you object to the recording, your option is to leave the session. And slides will be shared. During the talks, your micros and cameras are deactivated, and we're looking forward to interesting discussions. You will have noticed from the schedule that really a major part of our session is reserved for discussions both after the talks and at the very end, because we want to bring the community as a whole together. This particular session belongs to the remit of the Ontology Commons focus area on industrial domain ontologies. And here, the focus is on facilitating all kinds of interoperability, particularly semantic interoperability at the domain level. However, this must integrate into an encompassing framework, which in Ontology Commons is called the Ontology Commons ecosystem. And we are also looking into the role the top and mid-level ontologies can play at facilitating this kind of interoperability at the domain level. That much about the big picture. First, to introduce myself, which I didn't do. I am Martin Horsch from the University of Central Lancashire in Northwest England. Our speakers will be first Alexandru Todor from Fraunhofer Materials. His talk will be on fairness in material ontology. We're going to hear that right away. Simon Clark from SINTEF Industry will target one particular domain of knowledge, which is batteries, and he will comment on one particular development in that line and probably requirements that can be deduced from that. And then we have Alexander Behr from Technische University of Dortmund, the main ontology developer from the German National Research Data Infrastructure for catalysis-related sciences. So this will be concerning all domains of knowledge related to catalysis, and that also means chemical and process technology at large. What do we want? What do we want to discuss? You're free to bring up any relevant discussion points. These are only suggestions. What are the domain-specific requirements? What is missing? What are our needs? How do we get better interoperability and alignment between heterogeneous developments that we're having? And what can we do to organize joint work and improve the situation and harmonization? So in that, along these lines, the objectives, briefly, identify gaps, improve fairness, and improve perspectives for exploitation. We hope, since Ontology Commons is a coordination and support action, to ignite concrete activities that will bring us forward. And concerning development and concerning coordination and long-term collaborations to make sure that what happens at a national level and within an isolated domain of knowledge is properly integrated at a European level. With this, I hope not to take more time away, because technically there are 0 minutes reserved for this introduction. And I would hand over, thank you all for being here to begin with, and hand over the screen to Alexandru. Alexandru,
hello everyone. Just to make a small correction, the title of the talk was changed a while ago. It seems it didn't reflect it, but it's a more general talk about collaborative ontology development in materials science, also about fairness, but also about how to do it, what kind of tools and what kind of challenges we had in developing these ontologies until now. I'm Alexandru Todor. I'm the ontology expert for Fraunhofer materials. I have 12 years of experience in semantic web. I've been working on the topic of ontologies for thermochemical properties 10 years ago or so. I was also the administrator of the German chapter of DBpedia and the Mappings Wiki and other activities. I'm also a member of MARDA and the RDA group for material science. So I have a bit of experience, but I'm a computer scientist. The main developer for this toolchain that I'm going to present is Thomas Hanke. He's a material scientist and the digital officer of Fraunhofer EMVS, and he's going to be later on also in the answer and question session and can more deeply respond to questions that regard material science and the tools that I'm going to present. So my main work is part of the Materials Open Laboratory, which is a joint venture between Fraunhofer Materials. We have 14 institutes that are members of our group and 7 guests, plus the German Federal Institute for Materials Research and Testing, BAM, here in Berlin. The project has internal funding plus external project. It's based on 3 to 4 to 5 years of previous experience in developing ontologies and semantic approaches for material science. And our major goals in this project is to create an open environment for collaboration, first between our member institutes, create an infrastructure for this development, and publish our ontologies in that. The motivation mainly in material science is because there are lots of methods, industrial processes, and standards. There's a lot of background knowledge necessary to be able to interpret this data, to understand it, or to compare it to see if it's compatible. There's bad traceability. Usually you don't have a lot of provenance data, which makes working with the data harder. And a lot of the documentation is in natural language. It's unstructured, so it's hard to work with it. Well, the challenges in the semantic representation is actually you don't only need to represent the data, you need to represent the entire process behind it, at least in materials characterization. You need to know exactly how those values were determined, and each step of the process needs to be represented, and then you need to check if it was done according to a standard. You need to work with domain experts because they're the only ones who really have the knowledge to do the representation in the right way. Ontologists can't really do that. We're working with ontologies as a standard, so either we have existing standards that we need to convert into ontologies and make sure that those ontologies are really according to that standard, or we need to make these ontologies like a standard, because each material scientist has his own method and they differ slightly. So you need to have like a committee there and they need to agree in a way to represent it. So you need to work in groups, and we have bad tooling for this. So there's not a lot of tools for collaborative ontology development for non-experts. So how do we tackle this problem? First of all, we need a terminology provider. So one place where we can put all these ontologies, the existing ones, where they can easily be searched, found, so we don't start from scratch. We need collaborative tools that are visual, that multiple people can work together and directly see what they're working on, and don't require a lot of experience or training. We need a common ontology architecture so that all of the necessary building blocks up to the domain ontology already exist. That's well documented with examples, with ontology design patterns. And then we need data conversion and mapping tools, because in the end, you can only see if that ontology really works well if you have your data and you convert it into RDF, and then you can work with it. So we need a pipeline to combine all of these tools together that goes from the raw files to the knowledge base. So the first part, terminology provider. For that, we created matportal.org. Matportal is part of the Ontoportal Alliance, which is maybe everyone here knows BioPortal. If not, it's the largest portal for ontologies in the biomedical domain. There are other ones like AgroPortal, MedPortal, EcoPortal, another French BioPortal, and the newest one is Matportal. The features it offers, it's a collaborative ontology repository where everyone can register, upload their ontology. It automatically generates mappings to other ontologies. It offers version control capabilities, search, automatic and manual mappings. You can annotate your texts with those ontologies, so it has a built-in named entity recognition service. Multiple types of visualizations, a good documentation, and a really extensive API. Here are some screenshots of the different features, but you can just go to the portal and try it out. We're still working on it. We're building new features, but it's pretty complete, so it works well. So collaborative and visual ontology development. This is a tough one. So we really tried most of the tools in the landscape. There are dedicated tools like Web Protege, Mobi, which is actually was developed for material science, but it's like quite a complete platform. And Vocoreg, which is a Fraunhofer tool. And then there are adapted tools that just take existing visual diagramming or mind mapping tools like the InfoRapid Knowledge Base Builder, Microsoft Visio, or Dry.io. Then you can convert the output XML files that they usually generate into an ontology. After trying all of the tools, we chose to use Dry.io. Dry.io is an open source diagramming tool where you can just draw UML-like diagrams. And then with Chalk, you can convert those into an RDF representation of that diagram. Before we tried the knowledge base builder, it has better visualization, but it's closed source. So we built a converter that can take those SQLite files and can convert them into RDF. And we have another tool that we built that can take Microsoft Visio files and convert them into RDF. The reason we chose Chalk in the end was because it's open source, because we can extend it easily. It's just JavaScript, so we can work with that really fast. Common ontology architecture. So in the end, we really like the vision, the original vision of the Industrial Ontologies Foundry, which also foresaw how to combine the materials ontologies with the entire industrial ontologies. But one of the things that it didn't have like a domain ontology for all of the different materials ontologies. So there was MatOnto, which was originally Dolce, then it was converted to BFO, but it never was converted to support the common core ontologies. We also had our own ontology, another BFO-based ontology without any mid-level ontology, which we then converted to work with the common core ontologies. We call it the material science and engineering ontology. And then we have, this is like what they call in the IOF or used to call domain upper level ontologies. And then which just offers all of the common classes that we need for the domain specific ontologies. You can look at it, you can find it on Matportal and you can find it on GitHub. There are some examples of it on our GitHub repository. So now we come to the data conversion pipeline. So basically all of the method representations that we create with Chalk are in a method repository. They get automatically converted with the Git action into RDF files. All of the raw files that we have are in the resource repositories. There are CSVs. Then they are automatically converted to JSON-LD. And then that JSON-LD web CSV format can be mapped to the RDF representation of the method with our mapping tool. The mapping tool produces YARML mappings, which get converted to RML mappings. and go in the converter, the two different RDFs are combined. So the method representation RDF and RDF from our raw files, we get one RDF output, it gets validated, and then it gets deposited in the RDF repository. In order to achieve this, we had to build a couple of tools. The first one is the CSV to CSVW, which basically takes all of these non-standard CSV files that we have in the different institutes, automatically detects a bit of their structure, recognizes units and maps them to unit ontologies, and produces JSON representation of them. Then we have a mapping tool that then you load a method representation and the JSON file, and you can map the different columns in that web CSV to exact information entities in the MSCO ontology. The output is a YARML file, which then can be converted to an RML file, which then produces the RDF. So that's it. I can answer questions now if we have time. Otherwise, we can do it in the end of the discussion.
We definitely have time. Many thanks. So you can use the Q&A. I'm not sure if you can also directly speak up. Probably not. Probably have to take you upstage. So generally speaking, I would recommend you can write your questions already during the talk. Then they're already there when it's finished. So David Linke asks, let's begin with David's question. What do you think about the EMMO as a top-level ontology in comparison to the BFO?
Well, they both have different goals. So the BFO cannot do certain things, so it's not really useful, or you would have to extend it to be able to use it for materials modeling. But due to its documentation and existing ecosystem, it's very useful for engineering problems. And since our materials characterization issues and methods are mostly an engineering problem, it has been very useful for us. Plus, it has extensive documentation.
Next, from Gerhard Goldbeck, general question, what is your experience so far using these tools?
It's good. I mean, we had to work somehow, so we were working in really large groups with a lot of people, and in order to make progress, this is like the pipeline that we managed to glue together. It depends in the end which tools you're talking about. Our experience has been that there are not many tools, so we had to create them up to a level that we can work with them. So we're at the point where we can get work done.
Thank you. Then we have Alexander's question on ontology portals. There it is. What portal is based on BioPortal? How about OLS?
So we have looked, and I know all of these tools for more than 12 years. The ontology lookup service lacks a lot of feature that BioPortal already has. It's being used right now in some of the NFDI projects, but they're just re-implementing features that already exist and for a long time in BioPortal.
Good. Yeah, many thanks. Then let's proceed to the next contribution on the battery interface ontology by Simon Clark.
Great. Yeah, good morning, everybody. Let's see, I'll just share my screen here. Okay. Good. So Good morning. My name is Simon Clark, and today I'm here to talk about the Battery Interface Ontology, which we're developing in the battery community through projects Big Map and Battery 2030. And I'm here today representing a collection of colleagues with different levels of expertise. So I'm here somewhere in the middle. Ontology is a fairly new concept for me. I've been working on it for about 1.5 years now, and my core competence is in electrochemistry. But the group that we have developing this initiative spans a lot of different expertise. So we have very well-established people in electrochemistry, and some of the well-known contributors to EMMO participating in this initiative. So today I'd like to start by giving a kind of quick rundown of the battery industry today and why is it that we're here talking about ontologies for batteries. Why is it needed? Then we'll have a look at what's going on in the EU project Big Map and how these activities will affect battery data in the future, and have a short overview of the Battery Interface Ontology, which we call BattINFO for short. Okay, so to start, let's take a step back a few years to a simpler time in 2010. And back then, the average per pack kilowatt hour price for batteries was over $1,000. And over the last 10 years, we've been able to reduce that price quite substantially, almost 90%. And we've had a lot of success in improving manufacturing processes and making research improvements. And that's led to some pretty dramatic price cuts. Correspondingly, over the last 10 years, we've seen a steady increase in the uptake of electric vehicle sales around the world. And over the past 10 years, it's been fairly respectable growth, going from 0.2 million units in 2010 to 4.8 million units in 2020. But what we've seen over the past 10 years is going to be dwarfed by what will come over the next 10 years. And the IEA projects that by 2030, we'll have global EV stock of 140 million units under current policies and 245 million units under more supportive policies. So that's great news for electrification and for helping to address our climate change issues. And as battery scientists, we may look at this and say 90% cost reduction, huge gains in the market size. We did it, everybody. Good job. We can all go take a vacation now. And unfortunately, that's not the whole thing, because even though we've had a lot of success reducing price and improving the performance of batteries, now that is starting to ramp up around the world, it requires a lot of materials. So these are some common materials that are included in batteries: nickel, manganese, cobalt, lithium. And this is how much of those materials the battery industry consumed in 2019. If these gains until 2030 that we expect come to be, this is how much of those materials we will need in 2030. So incredible material demands, and this basically highlights the fact that we can't rely on our current lithium-ion battery technology for everything forever. In the future, we're going to need alternative battery chemistries that are based on more sustainable materials, and we can tune the properties of the battery to its application. So we need to build better batteries. What knowledge do we need in order to do that? Well, electrochemistry, of course, comes to mind, but it's not just that. It's, mechanical engineering and machine learning. And with all this gigafactory production going on, it's manufacturing and chemical engineering and process engineering. The breadth of knowledge that's really necessary in order to build better batteries is extreme. And as this topic starts to take off, it won the Nobel Prize for Chemistry in 2019. A lot of people in all of these different fields are doing battery research. And on the one hand, that is a disadvantage because there's so many different activities going on. But on the other hand, it does bring positive things, namely that all of these activities are generating a lot of data. And so as battery scientists, we're faced with this question. How can we distill this deluge of data into knowledge and meaningful action? And that is the focus of the battery interface ontology. The battery interface ontology is a formal machine-readable model encapsulating knowledge about electrochemistry and batteries. And this is based on the top-level elementary multi-perspective materials ontology, or EMMO. So we're aware of the challenge, and we're aware of kind of what's needed. But what does that really mean for us as researchers, and how can we start to propose alternative methods to deal with that? And this is kind of the focus of the EU project BigMap. BigMap wants to revolutionize battery development. So traditionally, the method of developing new batteries is very heavily trial and error based. You know, you make one change on the anode and then it's bad for the cathode, or you change something in the electrolyte and it's good for this thing but bad for that thing. And it just takes a very long time, and it's very expensive, and it's time that we just really don't have right now. So BigMap aims to take a more holistic approach and combine a lot of progress that has been made in different fields in, for example, multi-scale modeling and databases and common data infrastructure, autonomous robots for material synthesis and high throughput testing, and taking information from all of these kinds of different aspects and feeding it to a central AI orchestrated discovery platform. And immediately for the people in this meeting, the idea of interoperability probably shoots to mind immediately. BigMap generates a lot of data, but it's different kinds of data generated by different groups using different methods stored in different places. And because we're also aiming to implement autonomous methods, these machines need to be able to have some idea about the task that they're doing, the process that they're doing, and how that relates to other things. So this is the fundamental goal of what we're trying to address with the battery interface ontology, to provide a common machine-readable battery language so that we can bring all of the data and activities from these different fields together into a centralized approach. And to start, I'd like to do a little thought experiment, just very simple. And I'm going to say a word, and I'd like you to think about focus on the idea that comes to mind when you hear it. And that word is battery. Now, when most people hear that word, they think about something like this, right? Lithium-ion battery cell or cylindrical battery cell, something like that. But if you're from the EV industry, maybe you think about this, a big battery pack. Or if there's somebody here with military background, maybe they don't think about energy storage at all. They're thinking about emplacement for heavy guns. And batteries can also have different synonyms. So in Germany, sometimes it's called an accumulator, or in a different language. So if we want to create a kind of cross-European, cross-technical approach to share battery data, this is something we need to deal with. And this is, just the word battery. It's the simplest example there is. Within electrochemistry, there's a lot of these kinds of inconsistencies where we use very similar words to describe different things, like solid electrolyte interphase, pH, versus solid electrolyte interface, F, two different things. We use the same word, we use different words to describe the same thing, transference number and ion transport number. Or we use the same word to describe different things. So separator of the material versus separator of the space. So in order to build this up, we have a fairly well-established source of knowledge for electrochemistry. There are existing international standards defined by the IEC, which is standardized battery forms and requirements for, I think, about 100 years at this point. IUPAC has standards for electrochemistry that we can pull from, and there's a lot of well-established technical textbooks for electrochemical dictionary, electrochemical systems, so on and so forth. Over the past few years, as battery research has started to take off, there's been an improvement in checklists for publishing battery data in journals. So we can benefit from that to some extent, that things are starting to move towards a standardized approach. And we can move that from being plain text entries to ontologized machine readable information. So just showing an example of the types of relations that we define in BattINFO. So for example, if we take our top level definition of a battery, and we say, as we mentioned earlier, a battery pack is a battery and a battery cell is a battery. And a battery pack is the distinction that it's composed of or has some battery cell. Battery cell, in turn, has electrochemical cells, which have a positive electrode, a negative electrode, and an ion bridge. And of course, here already, the thoughts are probably coming to mind, anode and cathode. And this is something that we have to deal with, because the actual technical definition of an anode is where the oxidation reaction takes place. So if you have a rechargeable battery, it actually changes between whether it's charging and recharging. So we have to be careful not to introduce semantic inconsistencies in labeling things anode that are actually functioning as a cathode. But we can describe these as electrodes, which contain some active electrochemical material that must retain contact with the electrolyte, and that has to have some charge carrier on to shuttle charge within the battery. So simple example of kind of the foundational hierarchy that we're defining. And we can use this to do a few things, both within BigMap and broadly. So first is to define some common vocabulary standards and unique descriptors for concepts that are consistent, and using those to create machine-readable semantic battery data. There's currently a lot of software development going on in the battery field, developing different apps and databases, and they're developed by different groups, so not always to the same standards. So we'd like to try to find a way to apply the ontology to improve interoperability of apps, that if one group has a database and a different group has a modeling code, that they can use data interoperably between those. And finally, within the European research landscape today, there's a lot of different battery research projects going on. And we'd like to look into creating cross-project data management plans, so that we know if project A is generating battery data B, that can also be used by project C generating battery data D. So the Battery Interface Ontology is open and public, and we plan for the first stable release in February of 2022, so in just a few months, and that will be available on GitHub. In this activity, we face some challenges. It's a very big and ambitious initiative. Batteries and electrochemistry are a large and diverse field, closely linked with other domains. And we would really like to collaborate with a lot of the other ontology initiatives going on in Europe today, especially with regards to things like models and characterization methods, things we can all share and benefit from. We'd be happy to collaborate. We also face a challenge in engaging volunteer community in the development and lowering the barrier and raising the reward for use. Among battery researchers, the word ontology is kind of a new thing. Not very many people have heard of it. So we're trying to make it exciting and interesting and encourage people to adopt it in their data management. So to summarize, the battery industry is growing very quickly, and it brings together people from many different fields and domains. And a battery interface ontology is needed to unify the approach and make all of the data that we're generating fair. BigMap is developing a free community-driven ontology for battery data. And the first release of that ontology, BattINFO, will be made available on GitHub in February of 2022. So finally, thank you to the European Union for funding this activity, and thank you to all of our colleagues in the BigMap project who've been doing a lot of work. And yeah, thank you for your attention. Happy to answer questions.
Many thanks, Simon, for the interesting talk. So far in the Q&A, we have one question from Gerhard, but I guess this was still directed to Alexandru. I would suggest that we do this afterwards in the large discussion podium, however we want to call it. I also queued a question by myself. That would be, here you're integrating mostly, if I understand correctly, the data from your own consortium. that is necessary. What we would ultimately want is that all research data from the field become fair and can be used by all initiatives. I wonder if Ontology Commons could support this in any way. And I think also probably Alexandru in his coming talk might say something about this, because electrocatalysis is also included in NFDE4CAT and might help provide such data from journals, from all academic sources. What is your opinion? What could we do?
Yeah, exactly. And this is the ultimate ambition. I mean, in Big Map is one project, but Battery 2030 Plus oversees like 4 or 5 projects, and we have really good representation from the main institutes, battery research institutes in Europe there. So it's a good thing to get the activation barrier going. But I think in order to make it more adopted throughout the community, we need tools that make it easy for battery researchers to apply ontologies in their data management. I typically get when I present this to battery people, or people generating a lot of battery data, that they get like the concept of what an ontology can do, but the actual practical bits are difficult. Not everybody has the desire to do a lot of programming and to get into data science. So trying to develop some tools that make it easy for non-ontology people to apply ontologies in their data management would be very helpful.
Yeah, I hope we can get forward with this and stay in touch that this is actually done. Okay, next question by Gerhard. What tools do you use for development?
Yep. So we do all of the development in Protege, and the repository itself is hosted on GitHub, so we can share it there. We're also trying to blend this together with work that's being done in Ontology Commons and other projects through Jesper Friis is involved, and we're trying to bring in those activities here as well.
Okay, many thanks again. Then let's get ahead with our third contribution by Alexandru Behr about progress in NFDE4CAT.
Thank you very much. I hope you can see the screen right now. Good. So then I will start. And hello and welcome to my presentation on ontology development in process engineering and catalysis. My name is Alexandru Behr, and I will present you today the current status of NFDI4CAT, which is a German consortium regarding the catalysis research and focuses on fair data in this field of research too. So first I will give you today a short update on our general progress and then provide a short example on the ontology development I conducted at our lab. And so where we first started was kind of this picture. It's the data value chain in catalysis. And it's depicted here, and we took it as a starting point. And it's split into 3 general sub-areas, namely the catalysis data, heat transport and kinetic data, as well as process design data. And we even subdivided the catalysis data into 4 different sub-areas, namely synthesis, operando, characterization, and performance data. And as you can see here and here, some other NFDIs are also kind of combined with us too, or attached to us. So NFDI4Chem focuses on chemical research and thus is combined or is attached to the catalysis data, and NFDI4Ing for sure is somewhere connected to process design. But the goal of NFDI4CAT is to bring all these 3 areas presented here together by developing interfaces and common standards. And in order to achieve this, we engage in ontology development. So in the next step, we try to gather and find all the ontologies and semantic artifacts which are present today and are relevant to the respective areas presented. And so we collected them and classified them according to their importance for the digital value chain presented here. As a next step, we think that it's important to define some nucleation ontologies to get starting points for all those areas and to identify the top-level ontologies needed for this. And so that's the current status on that. in order to process this further, we decided that it would be too much for us, at least, to directly step onto the ontology pane. I present you here like the stepwise approach we identified, which we will have to do in order to get to the ontologies we need. So in general, we often have these formats, so lists, or if we are lucky, XML files regarding the data, but not furthermore. So we defined that the next step we want to reach is to establish SKOS, so simple knowledge organization systems, in order to write up thesauros and taxonomy files. That's important because we identified that there are many steps necessary with domain and IT knowledge combined in order to get to the ontologies. But in NFDI4CAT, most users and most members of the consortium are domain experts and not ontologists. I, for myself, am a process engineer, and I'm doing ontology design just for a year now. So that's this topic. So our first shot is to set up Catalysis-specific SKOS files. And in this way, we hope we can enable the domain experts in our consortium to engage in the task of gathering important domain concepts. So these thesauri are then used to identify fitting ontologies of the map I shown you before. And in the bigger picture, we also want to use existing and applied metadata standards in order to get some help on this stage of the informal hierarchies, and in order to get to the thesauri faster. And in an even bigger picture, we will use then those metadata standards combined with the ontologies and the data to obtain knowledge graphs, which can then be, for example, queried via a SPARQL query. So to the current workflow of NFDI4CAT task area 1, which is doing the ontology research, we already defined the existing ontologies and gathered them and clustered them even by topics of the Catalysis research. Right now, we are developing a template for domain experts, so which will be based on Excel, which is similar to a tool called WOC-Excel, which is available under GitHub and developed from an Australian group. And we are aiming to automate a workflow using Python scripts and these Excel templates to achieve an automated SKOS generation. And when we got these controlled vocabularies, SKOS files, and the existing ontologies, we then hope to get a better starting point in order to advance and enhance the ontologies which are already available, and to produce new ontologies for the Catalysis research. And our hope is that by the user acceptance, we will primarily extend the ontologies by concepts defined by the community. So we hope for a better acceptance by doing this. And for the next step of this presentation, I want to give you a short example on ontology development and use I conducted with the help of a bachelor student. So first I want to present you the approach we did overall and the aim of it. So we took some laboratory trials which were done at our laboratory, which were investigating biocatalysis and reactions in a small tubular reactor. Then we extended existing ontologies by the needed concepts, and afterwards, finally, we created this knowledge graph with the raw experimental data in a database and combined them together. So now to the workflow. First point was to analyze the laboratory trials and experimental data, collect all the objects and concepts which needed to be modeled, and analyze the lab trials. So we got a DOE of overall 12 experiments, and had to define all the physical components of experimental setup as well as the functional aspects of experiment, and thus came to classes, relations, and individuals which should be modeled. Afterwards, we analyzed all the existing ontologies I presented you before, and it shows or looked for ontologies which could apply or could at least help by defining at least some of the concepts we needed, and try to extend these ontologies. So yeah, we searched for an ontology where basics of process engineering were already included, because the lab trials were were based on process engineering, so that made sense to us. So in the first shot, we investigated OntoCape, the ontology for computer-aided process engineering, and chose this as an ontology to be extended because many concepts of process engineering were present in it. And it had also the advantage of being a modular ontology, such that we only had to import some of those modules. But the problem was that the concepts of biocatalysis and concepts of catalysis in general were missing, such that we took another ontology, REX, the ontology of physico-chemical processes, and recognized that the import of the whole ontology was not possible for sure, because they were set up differently, such that we had no choice but to manually integrate all the classes or the class hierarchies I've presented you here. So the reaction consisting of oxidation and catalysis was just implemented with their subclasses. And this was done by hand, which was kind of annoying, but the only way to go. So such that we had at least those concepts integrated into OntoCape. In the next step, we then extended these combined ontologies with classes, individuals, and relations we already defined in the first step, and by attributes in order to model the experiments. As depicted here, that's the rough setup of those reactors we investigated in the laboratory trials. And then in the individual selection, we were able to set up those properties regarding these reactors and stored them as individuals. As a next step, I also set up a database and stored the laboratory data, the raw data in it, gave it tags, and stored those tags also in the respective individuals regarding the laboratory trials, such that the database was kind of linked with the entries in the database. And in the last step provided some reasoning using the reasoner Hermit, and revised the ontology in order to obtain an extended ontology without further inconsistencies. And now I want to present you a short result. And so on the top right corner, you see the stats by the extended ontology. So in gray, it is depicted the imported ontologies, and black shows the extended ontology. And you can see that some classes were added, some relations, many individuals, and some attributes. And through the reasoning, it came up to about 1,000 axioms. And another further script I wrote was a Python script in order to obtain structured metadata or JSON files from the knowledge graph. So the ontology combined with all the individuals we implemented, and the experimental data from the database. And this was done with the help of SQL queries on the ontology, on the knowledge graph, and the database. And thus it was possible for us to obtain the raw data, not only, but annotated with the respective metadata of all the lab trials. And further research would be to apply a metadata standard in existing on this Python code, such that we get the metadata in a structured metadata standard way we desire. And with this, I want to close my presentation, and I'm ready for your questions. Thank you very much.
Many thanks. I was busy typing, sorry. Let's see if anything comes up. I have, however, myself have a question right away, and then we can go to the big roundtable afterwards.
Sure.
Let's first see what comes up by the others. My question was that what you mentioned, the conflict between OntoCape and REX, that looks to me like exactly the sort of problem where Commons can intervene and provide help and guidance and tools. Is there anything that you could identify where one could help in dealing pragmatically with conflicts, or I don't know?
Yeah, I think the first step would be, OntoCape and REX are kind of old ontologies and not that good maintained. I think it would help to focus on ontologies, or if you want to combine ontologies, then it would be a big help if you would look on the top level ontologies first. So this would be something I would argue for Onto Commons, that one could use. One could choose between different top level ontologies and then see which ontologies are present for those top level ontologies. So which are easy to be mapped and which are not that easy to be mapped or combined.
Okay, next question by Jacek about hierarchical ontology graphs. Can hierarchical, there we have it. Can they help in multiscale modeling? Does the hierarchy somehow reflect the hierarchy that we have in modeling?
I think they could help, but I'm not that clear what hierarchically ontology graphs and multiscale modeling have in common right now. So sounds good, I would argue, but I'm not an expert enough in this field in order to argue right now. So sorry about that.
Next from Gerhard. Let's wait for it to come up. Here we have it. There are many semantic tools for capturing experiments, animal, allotrope, more and more and more. How do you make a choice?
Yes, so that's the reason why we gathered all those semantic concepts and ontologies. And we are currently, or I'm currently thinking about developing something similar to BioPortal for the catalysis research, such that you can, when you have come up with a problem and you have gathered all the, or at least some of the concepts you will need in order to model this via an ontology, that you can search the existing ontologies for all those concepts, and it puts out the, let's say, 2 or 3 ontologies with the most hits, such that you will at least hopefully always get a starting point ontology. And if this search outputs none of the ontologies or just few hits within an ontology, then you would have to need to start from scratch. But otherwise, at least we are trying in NFT AlphaCat to achieve a solution where you will always find at least an ontology which is somehow similar to the topic.
Many thanks. And thank all the speakers. And now I guess it's the time to progress to the big round table. The same thing, just now addressing the whole panel. And there we have the question previously raised by Gerhard, which really everybody will have a perspective on. What to do about terminology agreements. And I might add to this, Alexander, you have mentioned this thesaurus discussion. Could something like this help in establish a terminology agreement? And but that's directed to everyone.
Okay.
Well,
Answer in any order. Who wants to begin?
Okay, then I will start because I brought it up. And yeah, so we are trying to activate most domain experts using simple Excel templates, because we thought that the user acceptance would be the highest if we choose a tool which everyone knows and everyone can use. So no specialized software for this, but just a simple Excel sheet where we tell the users where they have to entry their URIs, their classes, and before that we want to explain them what a class is and stuff like this. And yeah, then our idea is to port this directly to a shared vocabulary, such that we, in the first step, we have concise definitions of all the classes we want to build in an ontology. And I think it's of big help, because once you've got these concise objects or these concise definitions, then you can better check up in an ontology, are these classes defined there yet or missing?
Yep. For the battery interface ontology, we're taking kind of a similar approach, of course, with being able to reach out through Excel sheets and that kind of thing is also helpful for people who don't code per se. We're also trying a new approach, or that's the only one that I know of, but maybe there are others out there that I don't know of, using a wiki, a semantic media wiki interface. And I just pulled it up here, so if I could share my screen real quick, I'll just show it. And this is something that our colleagues at Fraunhofer ISC, Simon Stier there, has put together. And it's a wiki-like interface that most people are comfortable with, and you can go in and explore ontology terms. So it's all imported automatically from the ontology hosted on GitHub. And click on things in the map and get information here. And if somebody comes in and says, hey, I'm not so sure about that, I see that this term is missing, can we please include that? You can start a discussion, and that will automatically trigger the creation of a new issue on the GitHub repository, and then an ontology person can come in and address it. So I think it's a neat initiative where we're just kind of starting to get it rolled out and testing it and debugging it, but it should be helpful. Then also to supplement that, at least within electrochemistry and batteries, terminology there's a lot of resources we can pull from. Electrochemical Dictionary was just compiled by Bard, who's a very well-respected person in the field. IEC has standards and recommendations. So we try to stick to that as far as possible. In some cases, you get conflicts and we have to resolve it. But yeah, through a combination of that, I think is an approach that's working okay for us.
Okay, so I would like to add, we chose to go with proven tools and approaches. So the biomedical domain using BioPortal has proven to be very successful for that. It has these functions of automatically looking at the ontology, of raising discussions and issues, and creating like a community approach to propose changes to the ontology. It has proven successful in over 15 years, so we just applied that to material science. But I would say that the community is the most important thing. In materials science, it would be the RDA Materials Data IG group. So we've restarted motivating European partners to join there, because in the last years, Europe is kind of doing its own thing, and Japan, US, and Latin America are like separated from the EU. I don't know why. So we had like on Wednesday, the first reunited session of the RDA materials group. And then there's like the American Materials RDA, which is an open group, even though it's like focused on their version of the NFDI, which is the Materials Genome Initiative. But you can join those groups. They will accept you and create like communication between all these initiatives. So we can, in specific domains, like really have a lot of experts from different areas, because the terminology also differs from country to country. They use different standards, and basically that also changes the terminology, or they have different languages. So to actually have something useful, it really requires an international approach.
Yep. Yeah, I totally agree. And in the battery field, at least, and through Big Map, we've also, I'm American originally, have been working in Europe for about 10 years now, but we've been reaching out to the big national labs and researchers in the United States to try to create like a transatlantic approach that it's standardized, because it's in the battery field, like everybody's kind of moving in the same direction, but going in parallel initiatives. So trying to bring everybody together into a common approach.
Yeah, thank you. Next, we have Emanuele as a top-level ontology developer, he is asking a probably rather complicated question, but you can provide advice to the top-level ontology development. What would be an ideal feature that facilitates materials modeling ontologization and characterization in general? I do think that's a hard question to ask.
Well, what's really missing right now is documentation. So I would say we kind of know from the physics standpoint what is needed in top-level ontologies to do it. But right now, many of these ontologies don't have enough documentation because most of the domain experts have problems working with ontologies already. And then if you have a complicated ontology without like a lot of documentation, it's virtually impossible for anyone to use it.
Yes, I would agree on this. So I think that it's important that more documentation is taking place.
Yep.
Good. That's a clear answer. Surprisingly clear. Many thanks.
And just another thought that came to mind is documentation and training materials. I think would also be helpful. And it's along the same line. It's also documentation, but some explicit like YouTube tutorials and interactive kind of things to help guide people along would be helpful.
Good. While we see what is still coming up, I was having a question getting back to Alexandru. And generally speaking, I think Ontology Commons has the challenge. It's a coordination support action. It has comparably small funding in contrast to its objectives, which are huge. And so we need to figure out how to best involve people and anything else that exists. But now you specifically mentioned the RDA materials group. Maybe you can tell a few more words about it.
Oh, the RDA group basically tries to get the large communities involved, and there were different initiatives. Originally, there was also an initiative to build common ontologies and other things. So it's mostly like a connection point between the national or continental communities. They all have their internal communities like MARDA, like maybe Ontology Commons for Europe, or the NFTI, and the Japanese have their own groups, Chinese too, and something like that. But there's like monthly events or yearly events where we kind of present each other what each group does, and we try to find common projects or see like if there are like connection points, and then we can go either to MathSci, which is a common forum, or the MARDA initiative, or maybe invite them to Ontology Commons or in our work groups, and unite these projects that basically, so what we noticed this week is that we're all kind of working on the same things, but these are like internal projects. They're not necessarily documented. And until publication, there's many years of activity. So we're parallelly working on the same things, and it's just reproducing work. It doesn't make sense. So this is why we're trying to present the projects to each other, community to community, have like open discussion forums where everyone can join, find common points between all of these funded projects, and then work together to achieve something. It doesn't need to be this same ontology, same top-level ontology or something like that, but we can exchange the experiences and tools so we just don't reinvent the wheel and don't lose many years.
Other remarks on this from any of you? I guess that's very much to Simon. Please go ahead.
I was just gonna say I totally agree with the not reproducing work or doing the same thing twice. The more we can bring in other groups, especially from the US or Asia, the better off everybody will be.
Yeah, we can add that probably not everybody can see that. Gerhard in the speaker chat just wrote that he will also present Ontocomms to the RDA at its upcoming virtual plenary. And there's so many RDA groups, it's very hard to really stay informed about everything. But this is a good channel. What we need to have is a platform where we can have a long-term collaboration. I think this is one of our desired outcomes, and we must use such initiatives. Then next question comes from Michael Nöske. Similar direction, maybe. Features in top-level ontologies, or for example, in top-level ontologies that facilitate integrating the life cycle of a product and thus the end user.
Well, I mean, I would like to answer to this one first, because this was one of the main reasons why we chose the common core ontologies, because they already had like a product lifecycle ontology, and we could combine all of this stuff together. But I guess lifecycle of a product is modeled more at the mid or domain level. You kind of need but what you need is like a common architecture, a common ecosystem of ontologies that already exists and can integrate. So you need a good modularization, and you need a lot of ontologies at the mid or domain level to be able to base your ontology on that.
Yep. Yep. And within the battery field, that's a similar approach to what we're taking. The battery interface ontology is focused on battery cells and has more of a data focus. But we're also collaborating with Fraunhofer ISC to develop the battery value chain ontology, which is a kind of sister ontology for BattINFO that describes the process from mining through production and use and recycling. And the ultimate vision is that will help support these battery passport initiatives that are going on now. Because right now, if you have a battery in your car, or you send a battery for recycling, not all lithium-ion batteries are created equal. They contain different materials and they age differently. If you want to integrate it in a second use application, it really depends. And for recycling as well, if a recycler gets a truckload of batteries, it needs to know what's inside them so it can direct them. So the battery value chain ontology is a sister ontology to BattINFO that we're designing with that, or Fraunhofer's leading the development is working on to support that activity.
Yeah, I would agree on behalf on the catalysis research. It would not be advisory on every step of catalysis research to integrate a product lifecycle. Thus, I think it's okay to not depict it in a top-level ontology, but to, on a mid-level ontology, implement this product lifecycle.
So while others are still thinking, so I mean, anything about fair data quality assurance, or what I tend to call pragmatic interoperability, that would mean agreed ways of dealing with data that we could help adopt or develop, or that you think may already be in place?
Yeah, this in the battery field, at least, it's there's a conference next week dedicated to that topic, trying to standardize battery testing and standardize the methods that we use to generate data. Because I'm sure in many fields you can, if you're after any one specific quantity, there's an array of like 4 different or 5 different methods you can use to all get the same thing. And some have different pros and cons, and they're more expensive or cheaper, and it depends, which method you use to get it, and that's something that's kind of lost often in literature and in databases. So yeah, it's a discussion we're having in the battery field now, how to standardize the generation of those values, and I think it's something we can bring into the ontology development.
We specifically developed these ontologies to do that because in materials characterization, you cannot use like two tensile tests and that are from the same materials with each other if you don't know that they were determined in the exact same way. Even though many labs say, okay, we did it according to the standard, there's no way to prove it, and many times they don't really do it according to the standard, they just say so. So by having an ontology that really represents each step of the process, from the standard, it's really explicitly represented there, and you actually have to fill in the data for those, provide the metadata, and it's also computational. So you can go with the reasoner, and because each step and even the effects of the step towards the test piece are represented in our ontologies, you can go through a reasoner and see, okay, was that actually done according to the standard? Was each step is it conform? We can do a lot of validation checks if some values are not in the correct ranges for the standard. And we can even make conclusions. Okay, this step would have broken the test piece. It can't be tested any further, or many other things. So this is why we need to go really very explicit with those ontologies, map each step and process and all of the other characteristics of the step to actually make data fair and reproducible, and be able to use data from different labs together with the assurance that they were actually really measured the same way.
Yeah, that's a huge point in NFDI for CAT 2, which we didn't tackle yet. But yeah, it's already in discussion how we can achieve some kind of quality standard by the data we will share at the end of the day when all the ontologies are set. So yeah, there will for sure be many discussions regarding this topic, but we didn't tackle it in a whole yet.
Good. Right now, it seems as if, we have something again from Michael. There we have it. Who would be expected to derive requirements for ontologization? The end user, the ontologist, the end user, or the translator, or all?
From my experience yet in this young project of NFTI for CAT, I think the requirements are driven by the end user, because I've presented you OntoCape today. It is an ontology developed in the early 2000s, and it's more like established for an academic use. So Cape Open was developed starting from this, okay, but on this example of ontology, you could see already, okay, there was an ontologist who developed an ontology, but it was not used furthermore. And I think that's a huge point where the end users come into it. An ontology is only as good as the end user using it, because otherwise it won't get maintained. And I think it's very important to maintain an ontology once you have set it up.
More points of view on this?
No, that's not from myself. Yeah.
Yeah. Okay, now the interesting question about architecture from Gerhard. Your experiences, how to go about the architecture, where are the data items, the data instances actually stored? Is it in a relational database? Is it in a triple store? Is it monolithic or federated? Anything that you would want to recommend as a good architecture?
So for our projects, I think the metadata might be stored in a triple store, but the data for itself is most times too huge to store it, or it wouldn't be that practical to store it in a triple store, such that we will use separate databases. There also comes in the problem of intellectual properties. So yeah, that's a huge point at our project too. We got a whole task area regarding this topic. So yeah, I think we will stick with separate databases, but exchanging metadata.
Yeah, I can add to this immediately. Sorry about that. Because I was involved in this architecture development for NFD for CAD. The standard project is that major effort has been done for requirements analysis, and now the architecture specification is still an ongoing process. That means it has not been decided whether there will be the data items will be in a triple store or a relational database or anything. But there is the commitment, as Alexander said, is necessary to have a federated architecture for something like this, that in the end must be usable by all academic institutions in Germany. Yeah, now please go ahead, the others.
Yeah, and in Big Map we're facing similar issues. In electrochemical data, a lot of it's fairly small, and you can share it and put it in triple stores. Not so much of an issue, but there's also a lot that's quite big, and tomography data and huge data sets that are pretty much fixed to being stored at their home institution. So it's something that we're having to deal with, as well as having distributed data storage and sharing the metadata to point to where it can be found.
Yeah, so I hope you can still hear me. We also have an approach of distributed data, working with the national data spaces connectors. But in how far the data, so we convert all of the data in RDF, even the data files. We can do it. It makes no sense to put the entire data in the triple store usually, so the time series data and other things. But it should still be linked from the triple store and accessible, because we need to do a lot of machine learning or statistical analysis over it. So when we query the metadata, so the part of the data that really makes sense to put in the triple store, we need to be able to access it really fast.
Yeah, many thanks. I presume that now, as it looks, the audience is satisfied, and also including our rapporteurs. If that is the case, indeed, then I would like to thank you very much, our speakers, for your contributions and the discussion, and the whole crowd here. And this means that we still have time for smoke break until the summary session. Many thanks, and see you back there.
Great. Thank you for the invitation.
Yeah, thank you. Bye.
Thank you. Bye.